Today I'm going to present recent work investigating the basis of swap errors in visual working memory. So to briefly introduce swap errors, on the left here is an example of a queued recall task. In this example, the memory array is made up of oriented bars, and after a delay, memory is then queued with an orientation. And the participant would respond with the location of the item previously presented with that orientation. So in this example, when this is the orientation queue, the correct location to report would be of this item here. So in previous experiments using this kind of task, they found that responses not only cluster around the feature of the target, but also around the features of non-targets. And if a participant incorrectly responds with the feature of a non-target, this is referred to as a swap error, as the non-target feature is swapped in for the target feature. So as swap errors are reflective of a failure in retrieving the correct item from memory when queued with one of its features, the basis of swap errors may provide important insight into how features are bound into items. A key finding regarding swap errors is that they are more likely to occur to non-targets, more similar to the target in the queue feature dimension. So in this example, when the queue is orientation, you'll be more likely to make a swap error towards non-targets closer in orientation to the target. And this key similarity effect is consistent with the idea that swap errors are caused by a variability in memory for the key feature. So going back again to this example, if you were queued with this orientation, but the orientations that were presented within the memory array have all been stored with some variability, then you may report the location of this item here, as it is similar in orientation to the queue. One key aspect of this idea is that although you are retrieving an incorrect item from memory, the bindings between features of an item are remaining intact. A different interpretation of swap errors is that they are a result of a misbinding between the features of different items. So going back to this example again, you may remember the 5 locations that were presented within the memory array, but not be able to successfully connect them to the orientations that were presented within each location. So when you're queued with this orientation here, you may report the location of this item, even though the orientation is not similar to the queue. And an example of this type of interpretation is within the model of O'Brien and Lim, the interference model. And they include both a queue-dependent and a queue-independent source of swap errors. So in this task, you would expect to see both a proportion of swap errors more likely to occur to non-targets closer in orientation to the target, as well as a proportion of swap errors attributed to what they refer to as background noise, which would be equally likely to affect any of the non-targets. So the 2 questions I'll aim to address in the 2 experiments I'll cover today are 1, are swap errors a result of variability in memory for the key feature? And 2, can this explanation account for swap errors in their entirety, or are there likely to be multiple sources? So experiment 1 was a queued recall task, and the memory array was made up of 6 oriented ellipses. The elongation of the ellipses was set at one of 3 levels, with the expectation that as you increase the elongation of the ellipse, you'd be decreasing the variability with which orientation was stored in memory. So the elongation of the ellipse was kept consistent within a trial, and the area of the ellipse was kept consistent across changes in elongation. So after a 1 second delay period, memory would then be queued either with location or orientation, and the participant would respond with the other feature using a response dial. So 10 participants completed the experiment, carrying out 12 blocks over 2 1-hour sessions. And the first result I'll go through is the reporting of orientation. So this is when they've been queued with a location. And this result is important as it will show us whether the changing of the ellipse elongation successfully influenced the variability with which orientation was stored. So across the bottom here we have the distribution of errors when reporting orientation, and these are centered on the target orientation. On the top right here, we have the circular standard deviation of the response error, which is a measure of variability, and you can see that this is successfully decreased as elongation increases. Moving now to the non-target error distributions. So these distributions have been centered on the orientations of the non-target items, and these plots have been corrected for chance, so that any central tendency would indicate the presence of swap errors. But as you can see in all three plots, the distribution is close to uniform, suggesting that when reporting orientation, there were no swap errors. Moving now to the other condition, so this is when participants were reporting location after being cued with an orientation. So now you can see that again, the variability in the report once again decreased as elongation increased. However, in this condition, this is thought to be due to differences in the occurrence of swap errors. And this is supported when we look at the non-target distributions. So now when centering the distribution on non-target locations, we're seeing a clear central tendency in all three plots, suggesting the presence of swap errors. To generate a quantitative estimate of the swap error frequency, we calculated the proportion of trials where the location reported was closer to a non-target item than the target. And if the feature variability account of swap errors is accurate, then we would expect this to decrease as elongation increases. And that's the result we see here on the right. We then wanted to determine whether this swap error frequency could be explained by variability in memory for the cue feature. And we did this using a simulation. So the simulation ran through each of the location report trials, an example of which is shown here in A. And the first step of the simulation, shown in B, was to determine the orientation of each of the ellipse stimuli within a trial. And so in this here, the orientation is shown on the y-axis and location on the x-axis, and the cued orientation is represented by the dashed line here. And the next step in the simulation, shown in C, was to randomly select 6 response errors from the orientation report condition. And that's for the same participant and at the same ellipse elongation level. And these response errors were added on to the orientations of each of the 6 ellipse stimuli. And that was to simulate the variability with which orientation was stored. And the effect of adding on this error is shown here by the arrows in D. And then the last step of the simulation was to determine whether, after incorporating this error, whether the cued orientation was still closer to the target, or now it was closer to a non-target, and this is what has occurred in this example here. And if this is the case, then this trial would be categorized as a swap error trial. So the simulation ran through each of the location report trials 1,000 times, and the average estimated proportion of swap error trials is shown here on the right in blue. And as you can see, it closely fits the estimate produced directly from the data, and that suggests that the feature variability account could explain swap errors in their entirety. So to conclude experiment 1, the results do support the feature variability account of swap errors. However, the levels of elongation used did not produce great differences across conditions, and the question remained whether this result could be replicated in a feature other than orientation. So experiment 2 used the same task design as experiment 1, but rather than ellipse stimuli, we used random dot kinematograms. And the feature of interest was the direction of motion of the dots within each item rather than orientation. So the variability with which direction was stored was manipulated via the coherence of the motion of the dots in each item. And so this could be set at one of 3 levels, which was 30, 60, or 100%. And then after a delay, memory was then cued either as location or direction, and similar to experiment 1, they responded with the other feature using a response dial. So 10 participants took part in experiment 2, carrying out 12 blocks over 2 1-hour sessions. And now when we look at the reporting of direction of motion, so after they've been cued with location, we're now seeing a very clear difference across levels of coherence, and a clear decrease in variability as coherence increases. And similar to experiment 1, when location is the cue, there is no evidence of swap errors in the report. Now moving to the other condition, so when they're reporting location after being queued with direction, we're once again seeing a decrease in variability as coherence increases. However, again in this condition, this is thought to be likely due to the differences in the occurrence of swap errors. And that's supported when we look at the non-tag error distributions, and we've seen a clear central tendency in each plot, suggesting that swap errors are present when reporting location. And the same simulation was run as in experiment 1, with direction in the place of orientation. And here we can see that once again the simulation is, the results of the simulation are closely fitting the estimates produced directly from the data, and both significantly decrease as coherence increases. So to conclude, both experiments support the feature variability account of swap errors. And this finding has important implications for models of feature binding, which should account for this process. The results also suggest that the feature variability account could explain swap errors in their entirety, and therefore the inclusion of occurrences of feature misbinding was not required to explain the results. And lastly, I'd like to acknowledge Paul and Sebastian, who I worked with on this project.